Good afternoon, folks. Here's our challenge problem for today. We've done a lot of problems involving Newton's second law and doing some free body diagrams, but once things start to speed up, we find that things are rarely so easy that we just only have to do a free body diagram and Newton's second law. Usually there's something else that we have to do. And in this problem, that one is some geometry, some geometrical analysis. So to start off, here's what our description looks like. We have two identical 15 kilogram spheres, each 25 centimeters in diameter, that are suspended by two 35 centimeter wires. The whole apparatus is suspended by a single 18 centimeter wire, and the surfaces of the spheres are perfectly smooth, so we don't have to worry about any kind of like kinetic friction interaction between them. And we have to do two things in this problem. For part A, we have to find the tension in each of the three wires, and then for part B, we have to figure out how hard each sphere pushes on the other one as they're kind of resting against each other. And it can be hard to kind of determine what's going on in the problem description without a picture, so here's a picture I've created. And I know it's not a very good one, and it's not to scale. Things are not exactly equal in size here, but let's just go ahead and pretend, because PowerPoint can be a little difficult to work with. I'll start from the top and kind of label things as I go. The first thing is the length of the support wire. That's the wire here up at the very top supporting both of the other wires that are supporting the spheres. And that's the 18 centimeter value that we were given. The longer wires here that support the individual spheres, I'm going to call L main, and that's our 35 centimeter value that we were given. And you may wonder, what's the point of going through and creating this picture and labeling all these things? And the answer to that is once we go into a free body diagram and we try to include the tension of these wires, we need to account for some kind of angle, right? We know that they're not hanging directly down. They have to be at some kind of angle. So if we can't include that angle, we're not going to get at the right answer. So we have to do something to get at that. And what I would recommend as a first step is to draw the radius of the first sphere like this. And similarly, we'll draw the radius of the second sphere over on the other side. And if you pay close attention here, we have the beginnings of what appears to be an isosceles triangle. An isosceles triangle that maybe is not exactly to scale, but an isosceles triangle nonetheless, right? And so why do we care? Well, if I can find a way to close off this triangle, I can do a little bit of geometry manipulation to get at an angle, perhaps up here somewhere. And so what do I want to do to close off the triangle? I can use the radius of the spheres again, right? Radius 1 here, radius 2 here. And here's a label reminder that the radius of the spheres is 12.5 centimeters. And we're getting that by taking the diameter from the problem description and just slicing it in half. Speaking of slicing things in half, we have some kind of symmetry going on here between the two spheres. And so what I'm going to do is what a mathematician might refer to as bisecting this isosceles triangle. And I'm going to do that with this dashed green line here. Why do I want to do that? Well, it gives me an equal angle on both sides due to that symmetry. And since I know the length of the hypotenuse of the inner portion of this triangle, and I know the leg length, well, hey, I've got everything I need to know to employ the use of trigonometry to get at that angle. So how would I do that? Well, if I draw the inner angle or the inner triangle, excuse me, this inner left portion, what do we have? We have the sum of two lengths as the hypotenuse, and then the radius as the other length. I want to rewrite this as one single triangle, and to do that, I'm going to make it like this. We have the radius down here at the bottom, and then we have the hypotenuse here along the longest length. And why did I do this? Well, remember, we want to get at theta. That's the ultimate goal. And how can I do this using these two lengths? Well, I'll use the sine function. And just as a reminder, if you don't remember what the sine function is, it's the ratio of the length of the opposite part of the triangle divided by the length of the hypotenuse. And if we employ that definition in the context of our problem, the length of the the length of the opposite part of the triangle, excuse me, I messed that up there, is 12.5 centimeters. Okay, that's what's going in the numerator. And the length of the hypotenuse is 47.5 centimeters. And that's what's going in the denominator. Ooh, speaking too much, kind of twisting my tongue here. So why are we doing this, right? What's the point of using the sine function, right? We don't want sine of theta. We want theta, right? So how does this ratio, this expression help us? Well, if I want to get at the meat and potatoes of this sine theta function, I can strip off the outer sine function part by taking the sine inverse of both sides of this expression. And I'll actually do that in the next line here, right? So I'm taking the sine inverse of what was on the left-hand side, and that's equal to the sine inverse of what was on the right-hand side. And sine inverse of sine of theta, these two functions are inverses of one another. So they kill each other off, and we're left with the meat and potatoes, theta. Okay? So we could plug this into our calculator and get an actual value now in degrees for theta if we wanted to. I'm going to hold off for now, but just know that at this point, theta is a known quantity. It's no longer an unknown. Okay? We know what this value is moving forward. So what's next? We did all this geometry. We said that it was necessary because we were going to use theta with like tension. So I guess the next step is to do a free body diagram. So let's save a little time and put all those free body diagrams together. And when I mean free body diagrams, I mean we're going to have one for the left sphere, the right sphere, and the supporting wire. And so when it comes to sphere number 1, the one on the left, what are the forces acting on that? Well, we have the weight of the sphere itself pulling directly down. We have the tension in wire 1 that pulls up into the right towards the supporting wire. And we did this kind of, geometry acrobatics and split and bisected that, isosceles triangle. And, that's kind of represented by this dashed gray line here. And then we got what theta was by, doing the sine function and stuff. However, the problem is as it stands right now, theta is not in a good spot. We want theta to be like attached to the base of the tension vector. We don't want it attached to the head. It's kind of like backwards right now. So I would I would pay very close attention to the y-axis here and this dashed gray line that represents our bisected kind of portion of that isosceles triangle. Both of these lines are straight lines that are parallel to one another. So within that isosceles triangle, or at least in the context of this isosceles triangle, we are allowed to mirror this angle into the base of the tension vector, like this. That's totally allowed because these two lines are parallel to one another. And so we got what we wanted, right? We got our angle in the right location, so we can move on to the next force acting on sphere 1, which is what? Well, that's sphere 2 pushing back on sphere 1, right? Since they're both kind of like resting against each other. And that is it for the forces acting on sphere 1. Now, what about sphere 2, right? If you think about it, some of you who are watching may have this inkling of an idea in your mind that, hey, since there's symmetry involved, all these forces are just going to be, mirrored across the y-axis, and everything should be relatively similar. And you know what? If you did think that way, I would say you're absolutely correct, and I agree with you, right? There's not really much of a difference between sphere 1 and sphere 2, because we still have the weight of sphere 2 pulling down, and it's the same magnitude with the same direction as sphere 1. Instead of tension 2 pulling up and to the right, it's now up and to the left, which means that our angle theta would have been located here with the bisected part of the triangle right here. We're still allowed to mirror the angle to the tail part of the vector like we need it right here. And the force of sphere 1 acting on sphere 2 is the same magnitude as sphere 2 acting on sphere 1, but just the opposite direction due to Newton's third law. So no surprises there whatsoever. Literally the exact same thing going on, but just switched, right? Due to the perspective change here. One last thing though, the support wire. We have to account for all the forces that are acting on that. And it actually has 3 of them. We have the tension from wire 1 pulling down into the left, the tension from wire 2 pulling down into the right, and then tension number 3 pulling directly upwards, right? And I've included those equal angles that we solved for tension 1 and tension 2 here, right? And so what do we need to solve for? Why are we doing all this? Well, we need what? We need the magnitude of tension 1, we need the magnitude of tension 2 and tension 3, and then we need the magnitude of this sphere 1 on 2 or sphere 2 on 1. It doesn't matter because they're equal lengths but opposite in magnitude. So if we find out the value of one, we can just find out the value of other by just changing the sign if we have to. So let's start off with the sum of forces on sphere number 1. We're going to start with the sum of forces is equal to ma at the top of the page, where m is specifically the mass of sphere number 1. If we take the sum of forces in the x direction, what are we doing? Let me actually get a pen here. We're taking the sine component of t1. It's pointing in the plus x direction. How do we know that? Well, if I finish off part of the triangle here, here is the sine component. What is sine in this triangle? Well, it's the length of the triangle that's opposite to theta, so it's all the way over here. And it points in the plus x direction, so it's positive. So that's why t1 sine theta is a positive quantity here. What points in the opposite direction? Well, that's sphere 2 acting on sphere 1, and that's why it's negative here. Is there any acceleration in the x direction? No, because the spheres are not moving left or right, right? So there's no ma term over here on the right-hand side. That's just 0. It's gone. That's cool, though, because we can take this quantity, the force of sphere 2 acting on sphere 1, and just move it over to the other side. So now we have a direct relation between these two things here. So that's pretty neat. However, we can't do anything with it right now, so we'll have to come back to it later. Let's switch gears and move into the sum of forces in the y direction instead. So we have t1 cosine theta. What is that? So the cosine is the adjacent length relative to theta. So this line that I'm drawing right here, it's pointing in the plus y direction. So that's why it's positive in this sum of forces in the y direction. And what points in the opposite direction? Well, the weight of sphere 1. That's why it's negative. Does sphere 1 move up or down? No, it does not. So the acceleration in the y direction has to be 0. It can't be anything else. We can do the same trick as we did in the x part over here and take this weight of sphere 1 and move it over to the other side. So now we have another expression. But with this one right here, we're in a better position to play around and get to the tension in wire 1 because we actually know everything here already. We know the weight in sphere 1 because we know the mass of sphere 1, and we know the value of the acceleration due to gravity because we're on Earth, and we know what theta is, so we could just divide both sides of this expression by cosine of theta, which does this, and then we can exchange W for mg. So now we have the mass of sphere 1 times g divided by the cosine of theta. And I can plug all of my goodies in, and here's what we get. When we approximate to 3 significant figures like we need to, we find that the magnitude of tension 1 is 152 newtons. And not only do we get the answer of the magnitude of tension 1, but we get a double whammy here. This is pretty cool. We get this, and we can plug it in here. We can take this 152 number and plug this in right here, and we also know theta, so we get sphere 2 on 1 for free. Here's what I mean. I'm going to take the value of t1, plug it in here, and then I'm taking the sine of theta, and theta is this sine inverse of this ratio. And you might think, oof, that looks a little gross. Well, not really, because sine and sine inverse kill each other off, remember. So really, we're taking 152 newtons multiplied by 12.5 divided by 47.5. What does that give us? Well, 40.1. And that not only tells us the force of sphere 2 pushing on 1, but we also know, by Newton's third law, the value of sphere 1 pushing on 2. It's the same value, right? They're equal in magnitude, but opposite in direction. So there's T1, there's the sphere kind of pushing on each other. So we have 2 answers out of the necessary 4 that we need to get. So let's work on tension 2 next. And by doing that, we'll jump into sphere 2, and we'll do the sum of forces again, right? So we have the sum of forces is equal to ma, where we're looking at the mass of sphere 2 specifically. And when we take the sum of forces in the x direction, what do we get? Well, sphere 1 acting on 2 is purely in the plus x direction, so it's a positive quantity here. And when we take the sine of theta inside of the T2 triangle, what do we get? Well, that points over here to the left in the negative x direction. So T2 sine theta is this length right here, and it's pointing in the negative x direction, so it's negative in this expression right here. And sphere 2, much like sphere 1, it ain't moving, okay? Sideways or up and down. So the acceleration in the x direction is 0. And you know, we can move this term over to the other side, and we'll end up here. You can proceed and get T2 from this expression here. What I'm going to do is move to the sum of forces in the y direction and solve for T2 using the exact same process. So we can kind of ingrain that methodology in our minds. So remember before, sum of forces in the y. Maybe let's just take a look at kind of what's going on here before I move too far forward. What is the cosine component of T2? Well, that's the adjacent length to theta, which if I draw it using my little pen thing here, that's this length of the triangle right here, right? So T2 cosine theta points in the plus y direction, so it's positive in this expression here. And then the weight of sphere 2 points in the opposite direction, which makes it negative. And it ain't moving, acceleration is 0. Okay? So same thing like sphere 1, like sphere 1, excuse me. We're going to move the weight of sphere 2 over to the other side, which gives us this expression. And then we'll divide both sides by the cosine of theta. And we can exchange the weight of sphere 2 for mg. And since the mass of sphere 2 is the same as the mass of sphere 1, all of the goodies here are going to be the exact same as for what we did in sphere 1. So we get the same exact value for tension 2 that we did in tension 1. So that's cool, right? So it kind of verifies our hypothesis about the symmetry involved in the problem. We can do the same thing that we did for the last part and kind of take this piece here and plug it in to figure out what's the value of sphere 1 pushing on sphere 2. We know it should be that 40.1 number or whatever it was, but can we verify it? Can we prove it? Yes, we can, right? We take this number, we plug it in. Oh, hey, look, this looks familiar because it's the exact same thing that we had on the previous slide, which means if you don't end up with the same number, you have gone horribly awry. You should end up with 40.1 newtons because, remember, by Newton's third law, sphere 1 on 2 is the same as sphere 2 on 1. The only difference is the direction. So, in this case, we've verified our sphere forces acting on each other, and now we have T1 and we have T2. What's left? Well, we got to get T3. So let's move on to the sum of forces on the support wire. How do we do that? Well, F equals ma at the top, right? But now the mass is the mass of the support wire. We take the sum of forces in the x direction, and what is that? Well, the sine component of T2, right? Sine of theta of T2 points in the plus x direction there. That's why it's positive. And then in the opposite direction, we have the sine value of T1. So that's why it's negative. Okay, cool. We can flip this piece over to the other side, which tells us T1 sine theta and T2 sine theta are equal to one another. And since sine of theta is just a number, we're taking T2 times some number is equal to T1 times some number. And I can divide both sides of this expression by some number. And now this is a mathematical verification that T1 is equal to T2, right? It can't be anything else. So that's cool. That's kind of like the math way of saying, hey, you did a great job. Nice. You verified what you were saying previously. So, cool. Golden star for us. However, we still need to get T3. We're not done yet. So let's move into the sum of forces in the y direction. And as I can see, this is kind of cutting off on the screen here. If this is a little difficult to see, forgive me. We're taking the sum of forces in the y direction, which is what? T3, which points along the plus y axis. So that's positive. No angular dependence. Excuse me. However, we have the cosine value of T1, which is what? That's the adjacent length to theta. So that part of the triangle right there, that's pointing in the minus y direction, so that's why it's negative in this expression. And then for T2, we're doing the same thing. It's literally along the exact same axis. And that's why both of these are negative, according to this diagram here. And the support wire, like we said, it ain't moving. It ain't moving sideways, it ain't moving up and down. So the acceleration in the x direction and the y direction, both 0. And we can kind of clean things up a little bit because we just saw in the part over here that the two tensions holding up the spheres, they're equal to one another. They're the same. So we could almost just call it T, right? Every place we see T1 and T2, you could just say, hey, that's just equal to T. That's just the tension, okay? So let's incorporate that in this expression right here. So that way we'll have T3 minus 2 times the same tension in both, but the cosine value of it, that's equal to 0. And so what do we need to solve for? We need to solve for T3. We already know what t is. It's equal to, what we solved here for these two quantities, since they're equal. And we know what theta is. We already went through all the, the spiel of getting all that. So we move this piece over to the other side. And let's plug in everything that we have. Right? We saw that the tension in 1 and 2, same thing, 152 newtons. And then we're going to plug in the whole thing for theta. Right? I'm going to save a little space here on the screen and just not do that, but you can include that however you like. You can include the direct angle, or you can include the sine inverse of blah, 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 blah. But once you plug this into your calculator, you should get an answer very close to this number, once approximated to 3 significant figures. Okay? 294, or if you do a little approximation, maybe 293, should be in that range, around 293 and 294 newtons. And that is our value for tension number 3. Right? We got it. So now we have everything. We completely finished the problem. Let's move on to the solution card and kind of put everything all in one place so we can see how it all fits in and make sure we answered everything. So in part A, they wanted us to find the tension in wire 1, wire 2, and wire 3. Well, as we saw, the tension in wire 1 and wire 2, they're the same. They're 152 newtons. And for wire 3, it's a little bit bigger. It's 294. When it comes to the force of sphere 1 on 2 and sphere 2 on 1, we talked about how these are equal in magnitude but opposite in direction due to Newton's third law. And the magnitude of that force, or these forces rather, is that 40.1 Newton number. And that is the answer for that. Thanks for watching.